Hello viewers, in this video I would like to discuss numerical solution of algebraic and transcendental equations by bisection method. Numerical solution of algebraic and transcendental equations means finding the roots of algebraic and transcendental equations. Finding roots of algebraic and transcendental equations is very important as these equations occur in many applications of science and engineering. Zero of algebraic or transcendental equations means value of independent variable, generally x, which satisfies the equation, also known as root of the equation. An equation may have many zeros. Algebraic function. If each term of fx contains only the arithmetic operations between real numbers and x with rational power, then function fx is called an algebraic function. Transcendental function. A function contains at least one non-algebraic function, that is a logarithmic function, an exponential function, trigonometric functions, etc. An equation fx is equal to 0 is called algebraic equation or transcendental equation according to as fx is algebraic or transcendental function. The equation x to the power 6 minus 80x square plus 20 is equal to 0 is an example of algebraic equation, and the equations log x is equal to x e to the power x and 3 cos x minus x is equal to 0 are the examples of transcendental equations. Nonlinear equations involve polynomial of degree greater than 1, that is algebraic equation, or and may contain at least one non-algebraic functions, that is exponential function, trigonometric functions, and logarithmic functions, etc. Many numerical methods are available to solve the equation fx is equal to 0. To solve algebraic and transcendental equations, the commonly used methods are bisection, secant, fixed point iteration, regula-Falsy, Newton-Raphson, etc. Each of the above mentioned methods has some advantages and disadvantages over another method. To compare the methods, mainly the following points are considered: rate of convergence of the method, domain of applicability, number of evaluation of functions, that is number of computations, pre-computation step, etc. Geometrically, the nonlinear equation fx is equal to 0 represents a curve in the plane, and if the curve cuts the x-axis at a point, then the value of x at the point of intersection is called the root of the equation, and if the curve cuts at many points on x-axis, then all the values of x at the point of intersections are the roots of the equation. In the given figure, there is a curve y is equal to fx, and this curve cuts the x-axis at a point, and this point is root of the curve. But a pair of nonlinear equations or simultaneous equations, for example fxy is equal to 0 and gxy is equal to 0, represent surfaces in 3 dimensions. A point of intersection of these surfaces is the solution of the equations. Most of the time, it is very difficult to find such point of intersections in exact form. Therefore, numerical methods may be applied to get the solution. Now I would like to discuss bisection method or Bolzano method. Bisection method is the simplest iterative method to find a root of nonlinear equations, that is transcendental equations and algebraic equations. Finding a root of the equation is also known as solving the equation. If fx is continuous and real in the interval ab and fa and fb are of opposite signs, then the equation fx is equal to 0 will have at least one real root between a and b. In the figure, an interval x is equal to a and x is equal to b is given, and curve cuts x-axis at 3 places in this interval. It means the curve is having 3 roots. Now let's take one more example. Fx is equal to x to the power 4 minus 7. We calculate function value at x is equal to 0, which is minus 7. We take function value at x is equal to 1, which is minus 3. function value at x is equal to 2 is equal to 9. Therefore, there lies a root in the interval 1 and 2. Steps for finding a root by bisection method. Let us assume that the function f(x) be continuous in the interval ab. Find the initial values of a and b that would bracket the root. Calculate values of fa and fb. If fa into fb is greater than 0, that is positive, fa and fb are of same sign, then no root exists between a and b. If fa into fb is less than 0, then calculate x1, which is equal to a plus b by 2, and hence find fx1. If fx1 is equal to 0, then x1 is the root. If fa into fx1 is less than 0, then root lies between a and x1. Else root lies between x1 and b. Repeat the procedure till the result of desired accuracy is obtained. Here in the figure, curve has been shown and there is an interval x is equal to a and x is equal to b. Function value at x is equal to a is fa and function value at x is equal to b is fb. Now we will calculate x1, x2, x3 and so on till we reach to a root of desired accuracy. Here I would like to discuss one example. Find the positive root of cos x minus x e to the power x is equal to 0 by bisection method. Solution. Let's find the interval in which root lies. Function is given cos x minus x e to the power x. We calculate function value at x is equal to 0, which is 1, which is positive. We calculate function value at x is equal to 1, which comes minus 2.178, negative value. Thus root lies in the interval 0, 1. Now we calculate the midpoint, which is the initial approximate of the root. x1 is equal to 0 plus 1 by 2, which is 0.5. Function value at 0.5 is equal to 0.0532, positive value. Therefore, root lies in the interval 0.5 and 1. Now calculate next approximate root and repeat the process till desired accuracy. x2 is equal to 0.5 plus 1 by 2, that is 0.75. Function value at 0.75 is minus 0.8561. Now we write the calculation in tabular form. Table contains k, ak minus 1, bk minus 1, xk, fxk. K represents number of iterations, ak minus 1 is first end of the interval, bk minus 1 is second end of the interval, xk is the midpoint and fxk is the function value at xk. First two iterations we have seen in previous slide. In third iteration we replace 1 by 0.75 because function value is negative at 1 as well as at 0.75. We take midpoint of 0.5 and 0.75, which comes 0.625. Function value at this point is negative. In fourth iteration we replace 0.75 by 0.625 and take midpoint of 0.5 and 0.625, which comes 0.5625. Function value is negative here. Now we replace 0.625 by 0.5625 and take midpoint of 0.5 and 0.5625 and midpoint is 0.53125. Function value is again negative. We replace 0.5625 by 0.53125 and take midpoint of 0.5 and 0.53125, which comes 0.5156 and function value is 0.00655. Now we may stop here or we may do a few more iterations to get a better approximation of the root, and the root value is 0.5156 and function value is 0.00655. Now if we compare values of last two consecutive iterations, that is fifth and sixth iterations, the values are same up to first decimal place, that is 5. Hence the approximate root of cos x minus x e to the power x is equal to 0 is 0.5156, correct up to one decimal place. Thank you.